Everyone, and welcome back to this video. In the last video we talked about autoencoders and the complete paper in detail. Now in this video we're going to implement the same concept that is talked in this autoencoder paper here. So first we'll use PyTorch for this particular autoencoder implementation, and then we're going to use the MNIST dataset uh, for the implementation here. So first of all, I've already loaded my Google Colab and I have been provided a system with a GPU. So I'm going to start with the import. So first of all, we're going to import torch. So import torch. From torch, we'll import nn comma optim for optimizer. And for the data set, from torch vision, we'll import datasets and transforms, and then we'll import matplotlib.pyplot as plt. So these are the imports that we'll need. Let me run this. Now we will load our MNIST dataset that contains 70,000 grayscale images, that contains all numbers between 0 and 9, each sized with 28 into 28 pixels. We will then convert these images into the tensors and then create a data loader to fetch the data in batches for training. So for that we're going to do tensor underscore transform. We'll first initialize our transforms here. So transforms dot to tensor. Then we'll load our data set, and that will come from datasets dot MNIST. We'll store it in data folder, or I can do dot slash data. We'll use this data for training, and then this needs to be downloaded because the folder is not present there yet, or the data set is not downloaded. And then we'll apply our transformation to this particular data here. So we'll apply tensor underscore transform. Now we'll also initialize a loader which will come from torch.utils.data.DataLoader. Then I will connect the dataset to this. I'll use the batch size of maybe 16 for now, and then I'm going to shuffle my data before training it. So as you can see, the dataset is being downloaded here, and if I open you the file explorer, then we have this data folder that contains the MNIST data that I need. Okay, now we are going to define our autoencoder model here. So in this step, we define our autoencoder model, where it consists of two components. We'll first define our encoder. So the encoder will compress, it will compress the 784 pixels image into a smaller latent space representation, or latent representation. And then I'll be using fully connected layers for this one with ReLU activation. Okay, and then we'll have a decoder that will reconstruct 784 pixels image that will be from the latent representation here. And then at last we'll be using a sigmoid activation, as we talked about in the paper here. If you haven't seen that video, please, I'll keep a link down there, and then you can see that video and then come back to this implementation. So now let me define my autoencoder class. It will import nn.Module here. Now the init function for this one, I don't need all of these parameters. Let me also remove this return part here, and then I'm going to remove arcs and quarks inside from inside here. So first of all, I'll introduce my encoder block. This is going to be a sequential model with a lot of fully connected layers as well as the activations here. So first of all, I'm going to introduce a linear layer. That linear layer will take the image size of 28 by 28 and then convert it into 128 neurons. So 784 neurons goes down to 180, so 128 neurons. Then I'll introduce a ReLU activation to the output of this linear layer. Then again, that particular 128 dimension is going to be reduced to 64 dimension or 64 neurons. I'll again have another ReLU layer here. Let me put a comma below or before, and then another ReLU layer. I'll have another linear layer that goes from 64 neurons to 36 neurons, and then I'll again have a ReLU activation. Then I'll have another linear layer that goes from 36 to 18 neurons. I'll have another ReLU activation, and finally I'll have my final linear layer that takes me down from 18 neurons to 9 neurons, which will be the final shape of our latent representation here. So this is my encoder block. Now I'm going to do something similar for the decoder block. So nn dot sequential, so we'll have a linear layer that takes the value from 9 to 18 neurons. Again, we'll have a ReLU activation here. Then we'll again have another linear layer that takes it from 18 to 36 neurons. Another linear layer. Then we'll have one more linear layer after the ReLU activation that takes 36 to 64. Then another ReLU, another linear layer that takes it from 64 to 128. I think I missed a comma here, comma, another ReLU layer, and then finally another linear layer that takes it from 128 to 28 times 28, which means 784 neurons. And then finally I'm going to apply a sigmoid activation to this. So this is my decoder part. If you notice something here, we have kind of mirrored the exact thing that we have in the encoder into the decoder part as well, because in the paper we also talked about the format of this one. So this particular decoder is going to be a mirror representation of the encoder, having the exact number of neurons as we progress on the right side of this latent space representation here. Okay, so now that I have defined my two functions here, what I'm going to do is, I might have missed something here. Okay, there should be a comma. Now I'll define I'm inside a class, right? Okay, so I'm going to define a forward function which will take in the input x. First of all, I'm going to extract data from encoder block, passing x to the encoder block. Then let me write encoded and decoded here. Then I'll pass the same to the decoder block, and the value that will be passed into this decoder block will be the latent space representation, which is in the form of the variable or the object encoded here. Then at last I'm going to return decoded. So this is my complete model that I have here. Let me run this. Okay, I have no errors, which means the model I've defined is correct, but I need to verify it again. Then what we're going to do is, after defining the autoencoder, we'll create the instance of this model here. So how do we do that? We can do that using model equals to autoencoder. So this will create the instance of the model. Then we'll use mean squared error as a loss function, since it measures how close the reconstructed images are to the original input. So for our loss function, we'll use nn.MSC loss, And finally, for optimization, we are going to use the Adam optimizer with a learning rate of 0.001. And then we'll also introduce our weight decay, but we'll not keep the weight decay for now. We'll just write an optimizer dot Adam, uh, and then this is going to optimize the model parameters or the learnable parameters, and the learning rate is 0.001, or I can just write 0.0001, sorry. Or just 20 is, I think, sufficient for now. Okay, now that this is done, the instance of the model is created, and the loss functions and optimizer objects are also created. Now we have moved on to our training model. So in this step, the model undergoes training. Let's define the number of epochs. So the number of epochs, I'll keep it 20 for now. So the training process updates the model weights using the backpropagation and optimization approaches. And then the loss values are recorded during each iteration, or will be recorded during each iteration, and we'll also plot our losses to see how our model does over time here. So for now, for outputs, I'm going to keep output in my list, and then I'm also going to track my losses in another list here. So since I'm in a GPU environment, so I'm going to define my device and then instruct the model to use CUDA or GPU if available. Torch.CUDA dot is underscore available, and then if it's not available, we can use CPU. Okay, then I'm going to convert my model or the autoencoder class instance to our GPU, or transfer it to GPU here. So now I'm going to start my training. So for epoch in range num epochs, and then since we are working in batch because we have introduced data loader, so we need to load every batch of our data, and a single batch contains of 16 image, I guess. Let's see. Yes, it contains of 16 image. So what I can do is I can load images. I might not need the labels, and then I will load it from the data loader that I defined. Let me reshape my images to, and then add one more dimension to it, because I think the image is grayscale here. So we need at least 3 dimension for the PyTorch to take in the data and then process it. So we're adding an extra dimension on the front here. So, and then I'm going to transfer the data into the GPU as well. Now I'm going to pass it to the model. So model, and then I'm going to pass the images. The reconstructed images are present here. Then I'm going to apply the loss function. So loss function on the reconstructed image as well as the original images that we have. Then I'm going to set my gradient to 0 for the optimizer. I'll perform a backpropagation here, loss dot a loss, right? So loss dot backward, and then finally I'm going to do optimizer dot step, which is going to update my weights from the backpropagation process here. Then what I can do is I can append all of my outputs from each batch. Append epochs, images, I think I need one more bracket here, epochs, images, and reconstructed, which means it is going to include the original image as well as the reconstructed image to see how my model is working. Okay, and then finally I can print the loss for each epoch. So epoch plus 1, epoch plus 1, divided by epoch, and then epoch plus 1 divided by num epoch, num epochs. Then I can also print my loss value. So loss value will come from loss.item, and that's it. So finally, what I can do is I can plot my loss. I can plot my losses. So to do that, I'm going to do plt.plot losses, and then I'm going to keep a label for it as loss. So plt.x label is going to be epochs, and plt.y label is going to be loss. Then I'll enable the legend, plt.legend, and then plt.show. So let me run this. If we have no error in the code, the training should start. I think the code is pretty straightforward. Since the image is in 2 dimension, we have increased an additional dimension before the shape of the image. We passed it to the model via the encoder and then the decoder. From the decoder, we get the reconstructed image. We compare the reconstructed image with the original image using MSE loss, and then based on that loss, we perform the backpropagation here. So let me run this. Again, if we have no error, the training should start, and then we should pretty soon see the epoch result here. I think the training has started, and then it is going to take some time to see this particular result. So yeah, we have already started epoch 1 and the loss is at 0.039. We'll go for epoch 2. So in epoch 2, the loss has gone down from 0.039 to 0.023. We'll pause the video until and unless we complete epoch 20, and then I'll continue once the training is complete here. Okay, the training seems to be complete. It went from 0.039 down to 0.018. There were some oscillations in between. I tried plotting the loss plot, but I forgot to append the loss for each epoch into this particular losses uh, list here. But anyways, the model has been trained for 20 epochs, and now we'll see how the model works for some random data here, or if the model works reconstructs the data well for some random batch of data here. So let me write down the code for this one. So I have taken a certain batch of data from here. I've kept the model in evaluation mode and not in training mode. I don't want the weights to be updated for this particular set of data. I've converted the image to its appropriate shape, which is 1 comma 28 into 28, or 1 comma 28 comma 28, and then passed it to the model here, and then I'm plotting the reconstructed as well as the original images here. So let me run this, and then if we see, the top batch that you see here is the original image that we have, and then the image below is the reconstructed image that is done from this particular original image, converted into a latent space representation and then regenerated here. So the reconstruction looks quite good. What I'm going to do is I'm going to reduce the value of the latent space representation and then check if the reconstructed value degrades or not. So instead of keeping on 9 neurons, I'm going to convert it into just 4 neurons and then have 4 neurons here. Also, what I'm going to do is I'm going to append my loss here. So for this step, I'm going to do losses.append and then append the loss.item. I'm just going to train for around 5 epochs, not 20 epochs, because that is too long. So 5 epochs. So let me start. I've already loaded my data set. So or I can just start from the beginning. Transforms, model, objects, number of epoch, and training starts here. So again, it will take some time for the training to be done. So I'll pause the video, and then once the training is complete, I'll come back with the uh, losses for each epoch as well as the loss function. Now the loss curve should work well here. So I'll see you after the training is complete. Okay, the training seems to be complete. Since we have reduced the size of our latent space representation, so the loss has not gone down quite well, but it has gone down to some extent here. It started at 0.030 and then have gone down to 0.028. Now let me see if the reconstructions are as perfect as they were when the latent space representation size was quite large. So let me rerun this part again, and then you can see that now there is some blurriness in case of the reconstructed images that we have. Although the actual shape of our handwritten content or our actual image is being preserved, but with some changes. If you see the value 2 here, then you have some sort of curve in this particular case, but here you don't have a curve in the reconstructed sample. So the change in the latent space representation and the lower number of epochs has now created this form of blurriness, which indicates that our data set, that our reconstruction is not that perfect as it was earlier. So this is all for this video. I hope you understood the implementation very well. If you want, you can also try to implement some convolutional layers into the encoder and decoder, which might give you some good result than the fully connected layers that we have implemented here. And then if you get those results, do comment down below in the comment section and then share it with everyone. So that is all for this video. If you haven't watched my previous video on breakdown of this particular autoencoder paper, do watch that, and then also follow along this particular code to fully understand the concept of autoencoders and its implementation. So I'm going to end the video now, and I'll see you in the next one. Until then, happy learning.